So we'll take the third paper by Mohit Rajpurohit. It's on advanced QKD protocols and practical challenges. Mr. Mohit. Yeah.
Hello everyone, my name is Mohit Rajpurohit. I'm going to present my work on this advanced QKD protocols and the practical challenges associated with it. I am from CDAC Bangalore and in Quantum Technology Group. So this is the outline. First, we'll talk about the motivation behind this work, and then we'll see the quantum cryptography. What is quantum cryptography and advanced QKD protocols like measurement device independent QKD and the twin field QKD, and we'll discuss about this quantum hacking that can be hacked. This quantum QKD system can also be hacked by eavesdropper. Then we'll talk about this quantum random number generator QRNG and its integration to our hardware, to our this control electronic hardware system. We have developed this control electronics for this advanced QKD protocols, and later we'll study about some analysis we have done on this practical challenges in field implementation of these type of protocols. So over here, the picture is Professor Richard Feynman. Actually, he proposed this new way of doing computation using subatomic particles like photons and electrons by using their quantum properties such as quantum superposition and entanglement. One can solve a certain specific type of problems that cannot be solved using classical computers, which is like search algorithms and prime number factorization. As we know that the RSA, a classical encryption method, is based on actually prime number factorization that can be broken by a source algorithm, which with the sufficient larger qubit size, it can be broken. Uh, Now, the next picture is that this is a this golden chandelier. It is a superconducting based quantum computer. Now, as we said, that the security threat is imposed by the quantum, and when I say quantum, it is a nature, how a nature behaves. As I said, this security threat is imposed by a quantum. Solution is also given by a quantum itself in the form of quantum cryptography. Let's talk about the quantum key distribution. QKD is a secure symmetric key distribution technique whose theoretical security is assured by the laws of quantum mechanics such as no cloning theorem and Heisenberg's uncertainty principles. If you want to see a traditional way of QKD, there is a two parties called Alice and Bob, and theoretically Alice has a single photon source, or we can say a qubit that can be encoded in its quantum state. Information can be encoded in its quantum state, and that can be transmitted through this quantum channel. Uh, this quantum channel can be free space, and the fiber as shown in this picture. The first one is a free space or satellite based thing, and the other one is the existing telecommunication fibers that can be used. And the other side, the Bob actually decode the information encrypted by the Alice. As I have highlighted this thing, that there's a theoretical security or unconditional theoretical security, but there is a practical imperfections, and practical imperfections in the source side, imperfection in the encoding as well as the transmission. We know that these fibers and free space, they are lossy channels, and at the end this detectors vulnerabilities are also there. As I said, there is an imperfection. That imperfection in these physical devices that actually introduce the loopholes for the Eve and the eavesdropper to get the useful information from the Alice and Bob, the secret key, from a secret keys. Uh, to remove this loophole, we have to remove all the dependency from existing physical components. As I said, there are physical components are associated with this, and based on that, there is a DI is available. That is a device independent. There is no dependency on the devices. These QKD systems are there, but the DI QKD suffers with the highly complex system as well as the very low key rate. So, what is the alternative? Is MDI QKD? As I said, the last part. MDI is a measurement device independent quantum key distribution. When I say measurement device, there is a single photon detectors that actually used to measure single photons. Whenever a photon arrives at a detector, it actually get a detection. So, but SPD, these spads or single photon detectors are most vulnerable or weaker part of the this entire QKD system. So, at least we can remove the dependency from the measurement devices, and that is the part of this advanced QKD protocols, which is MDI QKD protocol. It removes the dependency from all the measurement devices present in the system. So as I saw in the fiber-based communication, uh, as I saw these satellite images, they are far, far away. If you see this uh, image, so there is a central station, and there are two stations, Alice and Bob, that actually send their quantum state to a central station where they uh, do certain kind of measurement known as the Bell state measurement. So this Alice and Bob in this picture, they look near, but actually they are far, far away, like hundreds of kilometers. I will explain all the well, I will explain all these blocks what exactly they are doing. But in this slide, we will talk about this Bell state measurement. Alice and Bob prepare this weak using a weak coin source. They send this phase randomization technique. They send the quantum state to a central station that is known as Charlie, and Charlie performs the Bell state measurement. What is Bell state measurement? It is a two photon based interference measurement. There is a joint projection of these two photons on one of the Bell state. The Bell state is known as this psi minus Bell state. Bell state is nothing but the maximally entangled states. So this MDI QKD has the advantage over the different traditional QKD system like phase reference based QKD system like DPS and COW. It is immune to all the possible detector based attacks there, and this has this inherent star type of topology. So it is MDI QKD is the best suitable for the longer networks. More than two stations can be used as a single central station for performing this QKD. And also it sustained higher channel losses because of this two photon interference. And as I said, this central station is actually an untrusted node. If Eve has the information, and if Eve has all the control over this signal, this station, detection of any of detector will not give any useful information to Eve, or it will not remove any it will not leak any information for our secret keys, and it is highly practical protocol. Other protocol is a twin field QKD protocol. MDI has a single disadvantage, which is secret key capacity is bounded by a Plov bound, which means that the secret key rate is linearly dependent on the transmittance of the quantum channel. So this twin field utility has all the features that MDI has. Along with that, there is a square root of dependency on the this transmission of quantum channel. So this blue line is actually a bound that cannot be broken by any other QKD protocol, where twin field is actually breaks this protocol and gives a longer distance. So these are again these two parties are there. Uh, they prepare the states. They feel like states, exactly similar states, and send it to a central station where Charlie this time performed a single photon interference. A photon interfered with the vacuum and announces the constructive or destructive results out of this detectors. Uh, Now let's talk about quantum hacking or attacks on the system. As I said, that the MDI and twin field, they remove the dependency from the measurement devices. So our measurement sites are totally attack proof. But the source we are using is a weak coherent source, and it has a finite possibilities, such as there is multi-photon emissions are there. So for that, what we generally use a decoy state protocol along with the weak coherent sources. Weak coherent sources is nothing but attenuated laser source. It means that when we have a pulse laser source and we attenuate such a way that mean photon number per pulse is less than one, uh, and we can, along with this thing, we send a decoy system, decoy state. Decoy states is nothing but lower intensity signals. So any effect or any presence of E will affect this lower intensity first, and that can be monitored by the parameters of the QKD system. Okay. So as I said, this imperfection of the practical devices leaves the potential loopholes and the E to spy the final secret key. So this is the approach which we can use it. But now the E is come with the new approach. This is together he come up with the three attacks. The one is the unambiguous state discrimination attack, and along with that, he can perform a photon number splitting attack. Unambiguous USD attack is nothing but he can discriminate these single state and the decoy states. And whenever he perform this POV measurements on the system, and whenever he discriminate this state, he will not disturb this decoy state and only get the whenever he get the signals. He will try to perform the photon number splitting attacks and get the useful information. So this was again a threat, and the solution what is given by a security patch or a patch. Patch is something like whenever we have a loophole, we give a patch to it to remove any leakage kind of thing. So we come up with this, not we, but researchers come up with this phase randomization of weak current sources. So phase of this weak current source is if it is continuously removed, the CSD and TNS attacks are not possible. So they are. So what we have done, we have experimentally done this. Discrete phase randomization of weak current source along with this decoy intensities. Uh, Now there is a word called random. How to bring a randomness in our source? So previously I have done some work. There is a quantum random number generation, and we can integrate it into our system. So there is a heralded single photon source. There is a nonlinear crystal. When we shine an intense light, occasionally some of the photon get down converted and generate a pair of photons. And these photons are actually shows that when we see the characteristics of these photons, they are truly single photons. And these are heralded single photon source because detection of one photon actually uh, heralds the presence of other photon. Now we have the single photons, and when we send it to a beam splitter, it has a 50-50 beam splitter, and when it has a 50-50 possibility, either it can reflect or it can be transmitted. It is a transmitted. We can say okay, it generate a bit zero, and when it reflect, we can say okay, it is a bit one. So based on that, we can generate a random bit string. Although there is an imperfection, we can do some randomness abstraction. After extracting this randomness, it clears all the nest randomness tests. So remember that now we have a random bit string, and we are going to integrate it with our existing hardware system. So this is the overall setup for MDI QKD. Uh, there is two party, Alice and Bob. They are far away from each other. They use this CW laser and the electro-optical modulators controlled by this FPGA boards. And the QLD is integrated with this source. So I'll go faster. So this is the FPGA-based control electronics architecture for our experimental data, experimental setup. This is FPGA board. First layer is actually a AXI interface that can be user command interface. We can give a user command and get some any information from this layer. Other thing is that whatever random number we have generated from the QRNG that can be integrated using a I2C protocol using this peripheral modes. It can generate a RF signal, RF output signal. We are currently generating a 1 gigahertz signal. It is a 1 nanosecond signal with the very fine 4 picosecond shifting. Apart from this, the last layer is actually generating a multi-amplitude signal that I will show you in next slide. So these are our experimental results. So what we have done this discrete phase randomization with the CW laser and the electro-optical modulators. So when these are 4-bit register values that are coming from the QRNG. Uh, so whenever a random 4-bit register will come, randomly it will select one of the phase slice from 0 to 2 pi, and it will randomize the phase. So we are doing in a 16 phase slicing. Uh, Apart from this, we are doing a phase encoding by using a 2-bit register. There are 4 different voltage output levels, and we can use this for phase encryption. Overall, this is the phase randomization optical signal. This is an optical signal. This has some uh, 1 gigahertz signal and can be shifted very finely. Last one, this thing is there is a bound that with the slice we compromise with the secret key rate. So we have done 16, so we are compromising with the secret key rate, but we are increasing the security. There are some practical challenges in the field implementation, especially when we do the photon interference. So there are this three, majorly three type of things we have to see about it. Uh, First one is the temporal overlapping at a central station. As I said, central station is far, far away from both the station. We have to do a nice perfectly temporal overlapping. They need to arrive at the same time at a base splitter, so they can perfectly interfere. And second thing is the polarization need to be identical for their interference. And the third is the phase of an optical signal need to be correlated, whether it is anti-correlated or correlated, whether it is zero phase or pi phase. That need to be taken care by using a feedback system and different two protocols. So as I said, there is a phase evolution that can be because of the optical sources. There are two optical sources, different sources are used, so that can be phase locked by a single reference laser source using optical phase locking techniques. For, for that thing, both the lasers are locked. And the second thing is the phase introduced by the optical channel. I said we are using a longer fiber channels. There is a phase evolution by this optical channels. So currently we are at here, and we have generated our both the states using this FPGA based control electronics hardware. There are this two protocols or two techniques to overcome with this phase introduced by the optical channel. We can send a time multiplex signal along with this quantum signal, and based on this high intensity signal we can actually manage to remove this phase evolution by done by this quantum channel. And second is the post selection protocol, where we can set an offset in post processing, and we can estimate certain parameters, and based on that, by minimizing these parameters we can actually get a nice phase evolution and remove this phase changes. So if I want to conclude it, so we have generated this phase randomized optical signal. I can say it is the initial quantum state using this weak coherent laser and the electro-optical modulator. We also have developed this control electronics hardware for this MDI QKD protocols. Apart from this, we are actively doing in practical what is the field challenges for the field implementations. for this kind of protocols. These are the references. Thank you, everyone.